All right, hello everybody. We're going to go ahead and get started. There's supposed to be 600 of you. Where is everybody? It's the last slot of the conference, we understand. Everyone, I'm Szumski. I'm a product manager for OpenShift at Red Hat.
And I'm Zibolski. I'm the lead software engineer for the metering project at Red Hat.
So today we're going to talk about collecting operational metrics across some really large clusters, 5,000, 10,000 namespaces, and go through some of the use cases for doing that, and then we're going to take a live demo at some of the technology, and we'll show you some reports running from some of these clusters. What we're going to talk about today is a component of our operator framework, the metering component of that, and I'll explain a little bit about what the operator framework is. If you're interested in demos, we're going to do some towards the end, so stick around, but we're going to kind of explain how we get to some of those demos first. So the operator framework is a set of tools to build operators. Operators are pieces of software that have specialized knowledge about how to run something. In this case, we have an SDK that helps you build these. So you take the operational complexity that makes up your application, you embed it in a piece of software, and we have a bunch of tools to help you do that, run testing cycles, all that type of stuff. We also have our lifecycle manager. This helps you run a number of operators on a cluster, 1, 5, 10, 30, and manage the lifecycle and upgrades of those. Then what we have is our operator metering. This is what we're going to spend the bulk of this talk on. And this is all about collecting operational metrics from the Prometheus stack that we have running in the cluster, and then turning that into useful reports for humans to do things with. All of this is hosted in a vendor-neutral GitHub org. We'd love for you to check out the code, get involved, file bugs, all that good stuff. And so for metering, the way that this works is we've got a few different things that we're interested in. The first is app-specific insights. These are custom metrics that your operators and the applications that they're running know about. Anything from the number of database tables you're running to if you need to do data rebalance operations, you might want to track that as look at node failures and that type of stuff, see how those affect each other. But also we have this really great data source on the cluster that's our pre-installed Prometheus stack. And this already knows about all the pods running on the cluster. It knows what namespaces they're in. So it's got a bunch of rich data that we can include kind of out of the box to help you get a bunch of reports. So I want to talk about some of those use cases and what this is useful for. So at the goal for this is really out of the box, you can have chargeback, showback. This is reporting on resource usage by a number of different metrics. And this really encourages the correct behavior of folks that are using your cluster. If somebody's requesting a gig of RAM, you want to make sure that they're using that gig because you can't use that gig and give it to somebody else. So we use cluster monitoring, like I said. So we've already got this really smart data source. So we're not tackling this huge problem. It's a little bit smaller of a problem. And then we want to make this framework extensible such that you get a report about RAM or CPU capacity or storage capacity. And if you want to further post-process that, we want to make that very easy to do. So before we get into it, this is kind of our end result. This is where we're going to get to. This is a CSV file that comes out of our system. And what this is looking at is a number of pods and namespaces across the cluster, what nodes they're scheduled onto, exactly how long that the pod was alive, and then getting some resource utilization out of it. In this case, we're looking at CPU seconds, as well as the actual dollar cost of that. When you have a really rich cloud billing API, you can actually then start computing these very easily and say, this pod cost $1.20 to run, that type of thing. So we're going to talk about how we get there. And so I mentioned we have these out-of-the-box reports. This is because these are the things that we can slice and dice based on our cluster monitoring. And so it's the things you can think about, Kubernetes needs to track for doing scheduling, CPU, memory, and storage. And then we can do either the request that you have in like your pod spec, the actual utilization as reported when that pod is running, and then the percentage starting to look at either total capacity and some ratios between some of these. And then we can do that on a pod level, a namespace level, a node level, and then the entire cluster itself. And you can picture that we've got reports for all of these, and you can mix and match everything that you want to do. So what this looks like under the hood is this is looking at 2 clusters that have this installed. I break out Amazon because we can do some dollar correlation there. So that flow is a little bit different. But you've got a bunch of clusters running. They have namespaces. There's pods in those namespaces. And we have metering software running that's looking at all of that and tracking it continuously. On Amazon, we can actually hit the Amazon billing API and say this pod was on this node, what type of instance is that, how much does it cost, what is the percentage of the pod is being used, or the node is being used by that pod, and can get to an actual dollar amount. So we're doing this on Amazon today. We hope to extend this to any rich billing API. And there's some really interesting use cases for doing this on bare metal as well. And then we want to output these reports to stable storage. We're using Prometheus as our main data source, and that doesn't stick around forever. You have to store it in RAM. You don't need to be doing that for months and months at a time. And so we want to output these reports at a scheduled interval to persistent storage, whether that's a PV on disk. You can go to like an S3 bucket, those types of things, whatever you want to consume this in your archival data warehouse. So I want to talk through some concrete use cases that are pretty interesting. This is our first one, which is you're just on Amazon, and you want to do show back to teams that are using the cluster. And let's just say every team has the standard 3 projects or namespaces on the cluster, dev stage prod. And then each team just has a blanket budget, let's say $10,000. How do you start computing this? Well, our metering software, you can use one of our default reports for looking at pod dollars like we just showed on the previous screen. And then you can either just dump that into Excel and start sorting columns, start adding things up. You could further post-process that into a BI tool of choice. There are a number of these out there. You could even start piping this into Grafana, start building dashboards, or even start sending off like Slack webhooks or anything you wanted to do. So these yellow boxes in all these diagrams are going to be any further post-processing that you want to do, start comparing reports together, take outside data that your company knows about or cares about, and start making this custom to your organization. So a really popular one is just shame underutilization. Everybody kind of wants to do the right thing when it comes down to it, but they just need to know that they're being kind of a bad actor on the system. So let's say we have a cluster or set of clusters that are used by 15 teams. And so we just want to say, hey, look, our threshold is if you request twice as much as you're actually using, you shouldn't do that. We're just going to let you know. So you can compare 2 of our reports and look at the ratio of that and have a piece of software that's doing some math. You could do this by hand. You could pipe it into something. It says anything above 2x, let's go send off a Slack webhook into that team's channel. Let's go send people emails. Let's put them on like a leaderboard. In this case, leading is not good. So you can do anything, and all you want to do here is incentivize the correct behavior. You're just wasting company resources. And then here's a use case for bare metal, and let's say we've got a few different clusters on bare metal, and you want to start looking at the usage across both of these clusters for a single team, and to also do some things like answer the question, how much RAM are we using? But you can also go a little bit further and start saying, well, actually, we know how much that RAM costs because we spend X thousands of dollars per machine. We also pay for maybe a bundle of bandwidth. Or we had this big NAS array that we use for storage, and we want to distribute that amongst all of those teams. You can start doing all of this logic, whatever kind of fits the needs of your organization, and then show it back to those teams. You could start shaming them on the storage costs. If this thing costs you 100 grand, it matters. So these are the types of things that you can plug in with this system. And so where this is really, really useful is for capacity planning. So set aside shaming people for a second, and we can use this knowledge about the cluster to know where the cluster is going. So you've got real-time utilization. You can start trending that over time. You can see where this is going. There's a number of things you can do here. The interesting use case for this, and this is what we're going to talk about for the rest of the talk, is this environment called OpenShift Online. These are these really, really big, highly multi-tenant clusters that OpenShift runs, and we do, these run real workloads, so you can sign up with an email address and get 2 gigs of RAM or a gig of RAM and go to town running real Docker containers. And we use these for scale testing for OpenShift. And so they're super highly multi-tenant. We can fit 5,000, 10,000 namespaces on these clusters, and they're really unique environments to start testing out some of this software. And so I've talked a lot about these built-in reports, but as I said in the beginning, we want to do this with custom metrics. All the things that make your applications tick, the things that are really, really important to them, you also might want to meter on those, even just doing capacity planning, but you might want to do things like telemetry, license enforcement. If you, say, built an operator that is commercial software and you want to distribute that to all of your customers, you need to know if you license per core, per database table, per gigs of RAM, per gigs of storage, whatever it is, you need to meter that and collect it. So this can form the basis of usage-based billing. And we do kind of a variety of all of these inside of Red Hat as well.
All right, thanks, Rob. So now that we've actually gone over some of the use cases we had in mind when developing metering and some of the things that we're trying to solve with it, let's go a little bit more in depth about how we actually achieve this, what technologies we've chosen, why, and also some of the challenges we hit. So one of the most important pieces of our stack is our query engine. We're using a database called Presto, which was written by Facebook. They market it as a distributed SQL engine that is designed for interactive processing, in particular for analytics. This is super useful for us because we're really just trying to get up to a place where people can really interact with our operators and our reports without having to, wait, until the end of the day, or, like typical batch jobs run maybe once per day or something, or even less. What we'd really like to be able to enable people is to actually iterate on these rapidly, make changes, customize things, potentially just use the things out of the box as well, but we want a lot of people in this cluster being able to interact with the system. The other interesting thing is that Presto actually doesn't really store any data. It's not traditional, like a traditional database that actually puts everything on disk and just treats it like a bunch of files. It's actually designed to be more of maybe a proxy in some ways. What it does is it's got this concept of connectors, which allow Presto to actually connect to other underlying databases. So what this means is you can effectively join database tables from many different database technologies. So you can have it connect to Hive, which I'll go into in a second. You can have it connect to Presto or PostgreSQL, MySQL, Cassandra, MongoDB, and you can have it join tables or documents across these different sources into a single, and through a single interface just using regular SQL, which is pretty powerful. The other component is Apache Hive. Apache Hive is also a SQL engine designed for SQL on Hadoop. We leverage this because it allows us to actually do storage and compute separate. We can actually have storage done entirely in S3 or HDFS or a local PV with read-write mini semantics. And at the end of the day, Presto is interacting through Hive to actually find where the data is, and then it's actually interacting with the underlying data wherever it lives. We also have a few operators. So the first main operator is the reporting operator. The reporting operator is pretty much what ties everything together. It is what talks to Presto, it's what talks to Hive, it's what talks to Prometheus, and the various cloud APIs to actually tie everything together. In reality, what it's actually doing, what that means is it's taking a Prometheus query, executing it against Prometheus, and then storing those metrics into Presto. At the same time, it's running these other SQL queries to actually run reports and produce the kind of actual information that you want to see, which might be what is the total capacity of my cluster for this duration of time, or maybe what is the percentage of the utilization at this time. The other piece is the metering operator. The metering operator is really what ties the different components together from a deployment and configuration and installation kind of point of view. It's what handles the life cycle. So you basically say, well, first you install the metering operator, typically through OLM or some scripts, and then at the input side, you're going to be creating a metering resource, a custom CRD. And this metering resource has a spec, just like everything else. It's kind of like deployment, and when you fill it out, it will actually output all these other components as deployments, stateful sets, secrets, and services for Presto, Hive, reporting operator, and even optionally HDFS if you don't have object storage for it available. So I want to talk a little bit about why we chose some of these components. As you might be wondering, we've made some interesting choices about using things like Hive or Presto, as you might imagine. Why not use something like Postgres or whatnot? One of the main things is that we want to integrate well with existing systems, not necessarily have to fully replace other systems that are good at what they already do. So one of the biggest pieces is we want to work well with Prometheus. Prometheus is really good for monitoring, collecting metrics, doing queries against that information. So we're taking full advantage of Prometheus as our actual part that is responsible for figuring out what's happening on the cluster, and we're using it as a data source to actually run queries against. The other piece is that we want to make sure that this works well on like bare metal environments and really any Kubernetes environment, which means it can't be a SaaS, it can't entirely rely on cloud APIs. I mean, you can use S3 as an optional piece, but it's not required. So that was a key piece. Related to that, though, is that we chose Hive in particular along with Presto because it means that we don't necessarily have to worry about the storage piece. There's a lot of storage technologies out there. A lot of the current relational databases around aren't designed to scale horizontally necessarily, or if they are, there's trade-offs that you have to make. So this allows us to actually have storage either outside the cluster, inside the cluster, leverage whatever you really want to use, and then it can do all the compute inside the cluster. And as I mentioned before, Presto is really unique in that you can just really work with the pre-existing data. There's not a import phase necessarily. I'll get more into that in a second, but what that really means is it's basically when you execute a SQL query, it's not like going to just download everything all at once. It's going to determine what that query needs to talk to, like actually look at, maybe in your S3 bucket or not. And it's going to basically on demand pull down the things that it needs for that query. So now that we've actually got a little bit of a better idea on how these components interact, let's talk a little bit about what the data flow looks like when it comes to metering. So the primary component that's doing most of this is the reporting operator. It's going to be talking to Prometheus, performing Prometheus queries, inserting that data into Presto, and then Presto is going to be using Hive to actually store that in something like S3 or HDFS or a local PV where it can be mounted on multiple pods. At the same time, it's calculating reports. So when you create a report object, it's typically with a schedule, something like an hourly schedule, a daily schedule, or longer. And in the background, it's running against the schedule, and it's running these SQL queries against Presto to actually calculate the results, and then also storing them through Hive in something like HDFS or S3. So I want to give you a bit of a better idea what this actually looks like from a user point of view. So right here, we have a report CR. The report is going to be using what's called a report generation query. You can see this referenced in the generation query field here. That query, I'll show you in a second. But at the end of the day, you don't really have to do a whole lot to use everything that's built in. These existing reports are really easy to create. You just say what query you want, you set the schedule, and create it. So here's an example report query. It's got some things omitted, but the main things you have to know is it's going to contain a list of columns so it knows what the data, the actual output's going to look like, and so it can validate things. But it's got effectively just a giant SQL query in there, using Go templates as a way to provide extension mechanisms. It's kind of like a macro system that allows the query to be slightly more flexible depending on what user inputs are being provided to the report and things like that, which I'll show you also in the demo. All right. So now I want to talk about actually what you guys all came here for, which is how we use metering on OpenShift Line, which are these really large clusters. So one of the very key things that we talked about earlier in the talk was capacity planning. OpenShift Online, as Rob said, anybody with an email address can sign up. No credit card, no payment details, nothing. You want access, you can get it. It's really designed for kind of smaller apps. We're not going to give you a huge amount of resources. By default, we give you about 1 gigabyte of memory and 2 CPUs. But the way you actually get that is you sign up, and then there's somewhat of a queue. These clusters are kind of a fixed capacity. Because we're not charging you for it, we can't just scale this out with infinite nodes. That costs money. We're not going to just spend endless amounts of money for people to run free apps like Bitcoin miners. So the way this works is we gate by capacity. If there's no capacity, you have to wait until there is. And so actually understanding what is being used, what's not being used is extremely important because we want to make sure people can have access to these clusters. So one thing that we did to actually solve some of these problems are we have teams that wrote a pod descheduler, which is basically designed to delete pods so that the cluster can be rebalanced in a more efficient way. Kubernetes doesn't have that by default. So we need a way to actually make sure the pods are running on well-sized nodes or in a bin that actually fits better for it. Another piece that we have is we have a component which is responsible for removing inactive users who haven't actually used the namespace or the quota we've given to them after a period of time of inactivity. And as I mentioned before, there's a default quota of a single gigabyte of memory and 2 cores. So what did we find? Well, one of the more interesting things that we found is that given the default quota of 1 gigabyte of memory and 2 cores, pretty much nobody actually sets their own resource limits or quotas. So that means we're going to be giving them the default that we set, which is 50% of their quota. And in reality, we found that the top 1,000 namespaces don't do anything with their quotas. They just leave it blank, which means they get half of their quota by default. And at the end of the day, we can basically come to the conclusion that most people aren't making customizations, and more often than not, we can actually see that our cluster being underutilized by these users. And we could also then maybe go to the conclusion that we could probably oversubscribe this cluster since the average person's not actually using everything we're giving them. On the same note, we looked at the people who are using the cluster. What we found was people who are using the cluster, which are apps that have real usage, not like idle, say I have 500 megabytes of RAM and I only use one, but actually are using some percentage of their memory or CPU. And in practice, most people are using around 85% of their limits for something like memory, and a little bit less for CPU since it's a little spikier. So in this case, this is a graph that we took from the data we produce. And as you can see, most usage for this period of about, I think it's 2 hours or more, it's showing that on average, people are using about 85% of their quotas. So what this tells us is that it's pretty well dialed in. If they're using one or like always at one, that would mean they're always hitting their quotas. And if it was something closer to 50% like our defaults, it means they're not really using all of it. So most of our most active users are getting a good usage, but they're not also hitting the quota limits, which you might expect. So what are some of the problems we encountered? It's a really interesting question. One of the biggest pieces that was difficult for us was actually ingesting this data. Prometheus is really good at this. It's got a good design for this, and it's basically pulling periodically all the data, or all the metrics and points in the cluster. We followed a very similar model with the reporting operator. Right now, there isn't a good way for Presto to actually natively make these queries for us. So what we had to do is we actually did have to import data, which is turning out to be about as big of a problem as we thought it might be. So at the end of the day, one of the problems we encounter is that importing these metrics gets backed up after a while, just because of the sheer amount of volume. Part of that's related to the high metric resolution. Right now, we collect at about a 60-second resolution for these clusters, which might be a bit of a low resolution for us, or high resolution rather. And it actually causes a really huge growth in storage requirements. Again, we're not necessarily building on top of a time series database here, so some of those efficiencies we gain from Prometheus are lost when we actually import the data. So longer term, we're hoping to actually leverage Prometheus more by hopefully actually having Presto make the queries against Prometheus directly rather than importing the data. The other issue we encountered was depending on the time of the day or what's going on in the cluster, the Prometheus instance isn't necessarily always going to be able to handle these larger queries that we want to make. And what's nice about making large queries is we can get a lot of data at once, but also potentially import more data at once rather than making smaller amounts of queries. So it affects our throughput as well. And then one of the last things that we've kind of hit was when we get these reports, they have everything we want, but sometimes that's too much information. With 5,000 namespaces, you can imagine with a report that runs on the hour, 5,000 namespaces times 24 hours, you get 120,000 rows for just a day's worth of data in the CSV file, and that can become a little bit less manageable. So we're looking at ways to fix that by probably making our reports support more inputs to do things like filtering by default, get the top N namespaces maybe instead of everything. That said, we also had some successes. We found that our Prometheus stack actually is going way beyond some of the typical recommended scaling values that even we document for Red Hat on OpenShift. In practice, we have much, much more than 7,200 pods on these clusters with a cluster of 5,000 to 8,000 namespaces, 1 to 2 pods per namespace, and you're definitely going over that amount. The number of nodes is about the same, but maybe a little bit higher, especially with Spectre and the lack of compute that we have available now in the cloud. And the storage requirements are also pretty high, but not that much higher than this. When it came to metering actually did provide us value. We were actually able to run these reports on these clusters with some tuning, and it worked really well with Prometheus at the end, despite some of the issues I mentioned before. All right, so next I want to actually show you guys what this looks like to interact with a real cluster. In this demo, I have a test cluster set up that's got roughly 2,000 namespaces. It turns out it costs a lot of money to run on gcloud, a 5,000 namespace cluster. So I hope you still trust me when it comes to 5,000 namespaces. But here we go. All right. So the first thing I want to show you is some of the reports that we've created out of the box. In this list, we have a number of hourly reports. Yes, I can. So now I'm going to have a bunch of terminals slightly. How's that? Now it's line wrapping.
It's all good.
All right, so each one of these reports is something that you can create out of the box. And what each one of these reports is doing is it's running on a schedule. Right now, it's going to run on the hour, every hour. And each one of these is running a very particular query, which basically specifies what it's going to do each time. So I'm going to show you one of those really quick. Let's see. Let's show you guys the usage for CPU.
Has anybody ever seen the custom printer columns for kubectl? It's pretty cool. So you can actually put in your own stuff, which is what we're using here.
So what I'm doing is I'm querying the report generation query custom resource. Actually, let me show you the whole list really quick. So we have a number of built-in queries. Some of these are more flexible than others, and some are just kind of building blocks for other queries, especially the ones that end in /raw. But the query I pulled out earlier here is basically just the spec dot. There we go. It's basically the spec.query for the custom resource that I showed before. Slightly better. The actual contents isn't super important, but I want you to understand that this is just raw SQL. There's a little bit of other stuff in there. There's some Go templates. It's there to make it flexible. In particular, this one is designed for a concept called rollup. That means we can actually have an hourly report, which calculates data on an hourly basis from raw data. And then we can have a daily report that reports on the hourly reports data, which actually it saves us a lot of computation because we're basically spreading out the computation over time. We don't actually have to go through the millions and millions of rows of the raw data when we've already calculated a summary at an hourly level. So what I want to show you is an actual report that uses some of this. What we have here is a namespace memory utilization and a namespace CPU utilization daily query or report. Each one of these is going to run every day, and then they have some custom inputs that actually tell us, I want to aggregate the results of another report. So let's go ahead and create that. All right, and then let's actually see its status. So we can see the namespace CPU utilization report has been created, and its status has been set to scheduled, so that means it's about to run or it's already running. And then we also can see it's got a table. And then, I know this is kind of hard to see, we can also see the last time it reported. I set it up to start from the 8th because that's when this cluster was set up, and I want it to calculate not only what is the current times data, but all the data that we already did have collected as well. So let's get the status one more time and make sure it's been updated. And we can see it's already caught up to a few days worth of data. It's now the 11th from the 8th. In a few seconds, it'll catch up to the 14th, as you can see all the other hourly ones have. And then while that's also running, I want to show you the other query, which is interesting, which is a cluster-wide version of the same thing. So the previous one was for namespaces. This is for the cluster-wide utilization for CPU and memory. Very similar. You can give some custom inputs. I want to aggregate these other cluster capacity hourly reports, as indicated here. So I'm also going to create that. And then let's check on the status. And so we have the namespace memory utilization one, and it's basically almost caught up, 1 day behind. And let's actually get some of these results. So I know this URL is somewhat hard to see, but it's basically we're using an OpenShift route to expose the reporting operators API. You can also use a load balancer service or ingress if you like. Right now I'm taking advantage of some OpenShift features that make it a little bit easier. And then the reporting API is basically a simple REST API where you can query the results in whatever format that you prefer. So right now we support JSON, CSV, and tabular format. So let's actually take a look at this in the tabular format really quick. And again, this is the cluster memory utilization report. So this report, right now, it's caught up, looks like to the 12th. I'll scroll to the right, don't worry. But the first two columns basically indicate the period that it was reporting on for that row. The third column is the total capacity available in byte seconds. So that's basically the actual of memory times the time that it was at that value. And then we also have the usage. And then on the far right, we have the percentage of overall cluster capacity that this is that is taken up. So beginning of the week, last week before I set up 2,000 namespaces, it was about 4% utilized, and now it's about 12% utilized. We also have some averages in case that's ever interesting for you, and same for the node counts. And then the same thing can be done for the namespace level report. So this one's going to be quite a bit bigger, and that's because it's going to have a row for each namespace per day. So this might take a second. And don't worry, I also have another view for this in a second. So what we have here is a bunch of clusters, or namespaces rather, and we have one for each row. This third column is the namespace, as shown. We have usage. Going to the right, we have the request. We have the percent utilization, or usage. And then we also have the percentage of the cluster's capacity in request. So a lot of these ones are basically idling. They're not doing a lot. They're actually the bad actors that we want to shame, like Rob was talking about. But we have some even worse actors that I want to show you. So I've already actually downloaded some of these reports as CSVs and opened them up in whatever BI tool you might want to use. In this case, I'm going to use LibreOffice. And so one of the things Rob talked about was actually just finding out what are people doing on these clusters. So what I've done is I've imported this into LibreOffice, and I've actually set it up so that it's going to show us the most recent data first. It's going to show the data that's most recent with a high request, but a low usage, which means things that are asking for too much and not using any of it. In this case, the top usage is metering. It's the only thing doing anything in this cluster, no surprise. Its usage is about 1% of the cluster, and it's requesting about 15% of the capacity, probably because I overscaled it to make this demo run really fast. But as you can see, the following ones are these cluster tester over allocated namespaces. I wonder what those are. So if we look at the usage, it's literally 0. These pods, again, don't do anything. They're literally the pods container. But they're requesting something like 7,000, or rather 717,000 CPU core seconds, which is something like, if I recall, 4 cores and like something like that, and over a period of time. And we can see its usage is really low, 0%, but its request is quite high, 8%. And that's out of the overall cluster capacity, meaning each one of these namespaces is basically adding up to almost a total of a quarter of this cluster's capacity. And we can do the same for namespace. In this case, namespace is a little different values, but it's very similar. We can see that they're asking for a lot of memory, but they're not actually using it. And then at the end of the day, if you want to know at a bird's eye view, what is my cluster looking like, maybe not at a namespace level, you can also look at these CPU or namespace or memory cluster-wide reports, which basically give you, on the 12th to the 13th, you had 4% of your cluster's CPU used, which is shown here on that row. And we used about 11% of memory in this cluster for the last day. All right, and I think that was it. Yeah, that's it.
Yeah. So thank you. I wanted to get a show of hands. Does anybody have a tool like this running against a cluster they're running today? Nobody? Kind of ish, maybe. A few people. Okay. Has anybody ever run into problems with pods that can't be scheduled because they ran out of capacity? Yeah, everybody running small clusters for dev tests, yeah. So you can imagine that this is a problem at any size, but it's a huge problem for us at large size. And the cool thing about this is we know that this will work against these really large clusters, so we can go ahead and hand this off to any sort of financial institution or big insurance company or whoever, and know that we're probably going to exceed their scale. And so as long as you've got a bunch of gigs to throw at Prometheus, you can really crunch that data and make it into something useful. So this all is open source. It's on GitHub. I think we've got a few links here. We'd love for you to try it out. This is a screenshot of our README. We're currently testing this with customers, but it works against any Kubernetes cluster. This is all very agnostic. We've got installation guides, guides for how to run reports. The reason we showed you all these SQL queries is because you can write these custom. We've handed it off to a customer, and actually, a few hours later, he'd already reported back that he'd been writing custom queries because he didn't like some of our logic. So it's really, really extensible, and so we'd love for y'all to try it out, get feedback, file bugs, all that good stuff. Thank y'all.